Now we're going to assess the quality of our FASTQ files. For that, we're going to use a tool called FASTQC. Before running anything, let's just organize our folders. So we have NGS course, and we're going to change directory for that. We have 01_raw, and we are going to create 02_trim. Inside it, so inside 02_trim, we are going to create one directory called FASTQC results. So we change directory for FASTQC results, and inside it we create two directories. One directory called pre-trimming and another directory called post-trimming. And we go one directory up, so cd ... And to check quality, we don't need the full FASTQ file. We can just use, for example, the first 10,000 reads. And since each read takes 4 lines, we extract 40,000 lines for 10,000 reads. So we use head and 40,000. So one directory up, (01_raw), where the FASTQ files are located, srr one.fastq, which is the name of one of the FASTQ files, output, and the name of the output will be pre-trim.fastq. And let's check. We have pre-trim.fastq. And now we are ready to run FASTQC. So FASTQC, we run it with 8 threads. So FASTQC, we output it, so -o to FASTQC _results / pre-trimming, and we run it on pre-trim.fastq, and we press enter, and it is done. Now we open the file with an explorer. So we go home, NGS course, trim, FASTQC files, post-trimming, pre-trimming, and we open the HTML with a browser. So we have the basic statistics, and we start with the pair-based sequence quality. In this case, the first 60 bases have high quality, so a quality higher than 30-ish. But from position 70 onwards, the quality drops significantly, especially after base 80, more or less. This tail degradation is common in Illumina reads, and this is why we trim low quality ends with the trimming we are going to do in the next step. So the conclusion here is that this sample clearly needs trimming after position 70, more or less, to improve downwards analysis. This plot shows the average quality per read across all reads in the file. So most of the reads have a high average thread score, close to 39-40. That means that the vast majority of the sequence have excellent overall quality. So we have a flag in per base sequence content. So ideally, this line should be flat and parallel. So small fluctuations are fine, but major variation means bias. In this case, the first 20 bases, more or less, show strong imbalance, probably due to adapters, priming bias, or overrepresented motifs. This is common in most of the reads, and we usually fix it with trimming in the first few bases. We expect this line to stabilize after trimming. So the per sequence GC content. What we are expected to see for a clean dataset is a roughly normal distribution and centered around the GC content for the organism. The organism here is Quercus lobata, and the genome content is around 47-46%, so it's more or less consistent with the species. So we have a flag for per base n content. So this plot shows how often an n appears in each base position in all reads. An n basically represents a sequence, nucleotide where there was not confidently assignment of a base, so a T, C, or a G at that position. So there's a small spike at 1, but immediately drops after that, so this is not alarming. This plot shows the length of all sequences in the FASTQ file. So here we see a single sharp peak at 101 base pairs, meaning that all reads have the same length, which is expected before trimming. We should not expect that after. About sequence duplication levels, the caption says percent of sequences remaining if deduplicated, 99.51%, which means that almost all sequences are unique, so no sign of overamplification or low complexity. We have no overrepresented sequences. And about adapter content, we have a flag here. So this plot shows the presence of adapter sequences along the reads. So mkdir transposes sequence from read the position 36 onwards, which is common on most raw reads. So these reads were not trimmed before they were uploaded to NCBI, and we'll clean this in the next step using a trimmer.